Alright, so just because water looks clear doesn't mean it's safe. But if it's cloudy, yeah, that is almost always a massive red flag. Welcome to this explainer. Today we're actually stepping right into the environmental lab. We're going to master a totally foundational civil engineering test, determining the exact turbidity of a water sample. So what exactly is turbidity? Well, essentially it's just that cloudiness or haziness you see in water. It's caused by all these tiny, often invisible suspended particles, things like clay, silt, maybe some finely divided organic matter. And if we want to ensure our water is actually safe and treatable, we can't just eyeball it, right? We have to quantify that cloudiness using a very specific metric, Nephelometric turbidity units, or as we usually call it, NTU. To actually measure this NTU, your best friend on the lab bench is going to be the Nephelometer. Now, alongside this main device, your setup needs a few other things. You'll need a sample cell, we usually just call that a cuvette. Your actual water sample, of course, some distilled water, standard reference solutions, and, oh, this is absolutely crucial, a strictly lint-free cloth. Seriously, do not overlook the cloth. Okay, so to make this instrument work accurately, we need a solid baseline. For your absolute zero, you'll just use filtered, turbidity-free distilled water. Easy enough. But what about the upper limit? Well, we can't just use natural dirt because it's way too inconsistent. Instead, you're going to mix analytical-grade hydrazine sulfate with a hexamethylene tetramine solution. Basically, this chemical reaction creates what we call the formazine standard. It's literally a perfectly consistent, universally recognized synthetic cloudiness. Pretty cool, right? Now, here's the clever part about how this whole setup works. We aren't just looking at how dark the water is. The Nephelometer operates on a very specific optical principle. It actually shines a beam of light straight into the sample. But, and this is key, the sensor sits at exactly 90 degrees to that beam. So it only measures the light that gets scattered sideways by those suspended particles. Basically, more scattered light means a higher NTU. Alright, before we actually test anything, we've got to tune our instrument. First things first, switch the Nephelometer on and just let it warm up a bit so the light source stabilizes. Then, insert a cuvette of that turbidity-free distilled water we talked about and adjust the dial until the readout is, you guessed it, exactly 0. After that, swap that tube out for your prepared 100 NTU formazine standard and adjust the upper dial to read exactly 100. You'll want to repeat this just to make sure your baseline is absolutely rock solid.
Okay, now for the main event, your actual sample. You're going to gently invert or shake it just to distribute those particles evenly. But, and hold on a second, you have to wait a moment for any air bubbles to escape. Why? Because bubbles will scatter the light and give you a completely false high reading. So pour the sample into the cuvette, and then, remember that lint-free cloth? Grab it. You need to meticulously wipe down the glass exterior. Honestly, even a single microscopic smudge or a tiny bit of fingerprint oil will scatter the light and completely ruin your accuracy. Once that glass is pristine, pop the cuvette in, close the lid to block out any room light, wait for that digital reading to stabilize, and boom! Record your NTU.
You'll be recording all your data super systematically in an observation table. Now, one thing to keep in mind, if your sample is heavily polluted and spikes past 100 NTU, the sensor essentially gets blinded by all that scattered light. If that happens, no worries. You just have to dilute the sample with your turbidity-free water until the reading drops back down below 100. Then you'll log the diluted NTU reading, the volume of water you added, and the original sample volume. Throw all that into the standard dilution formula, and you've got your true final value. Your experiment basically wraps up once you can confidently state the precise turbidity of your water sample. But look, this is not just some random number in a lab book. The real-world application here is massive. High turbidity can literally act as a physical shield in water, literally protecting harmful bacteria from disinfectants like chlorine. So this exact NTU figure you just calculated, it is absolutely heavily relied upon by civil and environmental engineers out in the field. They use it to determine chemical dosing and to design the actual filtration systems for our water treatment plants. So, as you wrap up your lab work today and wipe down your station, I want you to ask yourself something. How might slight variations in this incredibly precise calibration process, say you left a single forgotten smudge on a cuvette, or maybe your formazine mix was just slightly off, how could that alter the safety tolerances of an entire municipal water network? It's kind of wild to think about, right? Precision in the lab literally translates directly to public health in the real world. Thanks so much for joining me on this explainer, and hey, enjoy your time in the lab.